All right, we're done with hydrations for the time, but we're not done with reactions of alkenes. We got two more to go through. So let's move on to halogenation. Adding a halogen, Cl2 or Br2, across the double bond. One chlorine will go on one carbon of the double bond, the other chlorine goes on the other carbon of the double bond. That gives us a vicinal dihalide. A few notes. It's only useful for Cl2 and Br2, not F2, not I2. There are no rearrangements, no carbocations here, and only anti-addition of those two halogens. So here's the general mechanism. If we have the carbon-carbon double bond and X2, the double bond attacks one of the halogen atoms, and one of the lone pairs on the halogen atom at the same time attacks the other carbon of the double bond. So that'll form a single bond between this carbon and this halogen, and then another single bond between the halogen and this carbon, and at the same time that bond breaks between the two halogen atoms. So all this is happening at the same time. This bond is forming, this bond is forming, and that bond is breaking, and the carbon bond, pi bond is breaking all at the same time. And it makes this beast right here, two carbons with a bridging halogen. We call this the bridged halonium ion. And when we look at this, we note this bridged halonium ion looks a lot like a protonated epoxide, doesn't it? Didn't if we had carbon-carbon and oxygen, and we added a hydrogen to that, protonated, have positive charge, doesn't this bridged halonium look kind of like a protonated epoxide? Well, keep that in your head because it kind of reacts like a protonated epoxide. So we've got the bridged halonium is unstable. Our other halogen, X-, halide ion, will come in and attack one of the carbons, breaking that bond. And so we've got one halogen on this carbon, one halogen on that carbon. Note that this is kind of SN2-like, meaning that this halogen must attack from the back side because this bond does not break until this halogen attacks. So it's anti-addition only. All right. So that's awesome, you say, but what about stereochemistry? Well, good question. Note, if we had this cyclopentene and added Cl2 to it, we've got one chlorine up coming from the top, one from the bottom because it's anti-addition. Note, we've got two chiral carbons. This is not a meso compound because there's not a mirror symmetry from this top to the bottom. So this is chiral, this is optically active. We have to make the enantiomer. Note that we do not have to worry about diastereomers because this is anti-addition only. Diastereomers would come about if we had syn addition, and we do not get that here. Okay. So let's look right here. What would happen if we took cis-2-butene versus trans-2-butene and added bromine to it? Note, here's the cis, and I'm drawing this kind of flat. These hydrogens are coming out towards us. The CH3s are going back away from us. This is a flat molecule. The double bond will attack this bromine, form the bridge halonium. The bromide will come in and attack one of the carbons from the bottom side. Anti-addition, so we'll get one bromine up this way, one bromine down that way. And okay, that's chiral, that's chiral. Are these two enantiomers? If we draw the mirror image, and the answer is yes, that these, ooh, I've got these bromines here. How can you tell? Ooh, how can we make sure it's not a meso compound? Up here it was kind of obvious. If we had a mirror symmetry on this and this, we know this isn't meso, but is this meso right here? Well, if I move this bromine up here, I can see that my methyl group that was going up and back with 180-degree rotation is now coming towards us and down. This one's going away from us and down, so that would not be the mirror image. So we can say, I need my enantiomer here. But note if we start with the trans-2-butene and add Br2, same thing, we're going to add one bromine to this carbon, one bromine to this carbon in an anti-fashion. But note, if I rotate this bond 180 degrees, so this bromine comes up, note that this methyl group here that is coming up and out towards us. It's going to end up going down and away from us. And we can see that, uh-oh, this is a meso compound. This molecule is a mirror image of that molecule. So no enantiomer here. When we add Br2 to our trans molecule, we only get this one product because it's a meso compound and it is not optically active. Our last reaction for this chapter is forming halohydrins. Someone said, hey, let's make the best of both worlds. Let's add halogens and let's add water to our molecules. So if you take an alkene and add a halogen and water at the same time, both of these in there together, then you'll put a chlorine on one, a halogen on one carbon of the alkene, the OH on the other carbon. Well, how does this work? First thing to note, no catalyst in here, no acid. Which means if you had an alkene and water and no acid in there, nothing would happen because water will only be attacked by a double bond. This only happened with acid catalyzed reactions. But we do know that an alkene will attack a halogen, a Cl2. So if you put Cl2 and water, both of them in there, the only reaction that will occur is a double bond will attach the halogen to make the bridged halonium ion. Now, most of the time when you made the bridged halonium ion, the Cl minus, our halide, will come in and attack that carbon. However, if we have a whole bunch of water in there, such that the amount of water is much larger than the amount of this halogen, this halide ion, then the reaction favors the more concentrated reactant. And so water will come in instead of X minus to kick off that, and we end up with water on one carbon, the halogen on the other. Of course, this is protonated. Got to get a deprotonation reaction to get our alcohol, our halohydrin. So normally we're going to have water as our solvent, because if we do that, just have a whole bunch of water, throw in a little bit of alkene, nothing will happen. Throw in a little bit of halogen, we'll start making bridged haloniums, but then we have so much water around, since it's a solvent, the water will come in and form our halohydrin. Now, some people say, well, I want to control it better than that. And we found a way if you want to put a bromine on there. If you've got your carbon-carbon double bond and you want to put an OH on one carbon and a bromine on the other carbon, we've got this reagent NBS, N-bromosuccinimide. It's this beast right here. N-bromosuccinimide in DMSO and water just goes through a nice little reaction. We won't go through it too much, but it's in equilibrium with Br2. So this kind of breaks down into Br2, but the equilibrium favors this. So this reaction, this molecule is in equilibrium with Br2 and another product, but the equilibrium favors this. So our concentration of Br2 is very low due to that equilibrium. The main deal is here, NBS is just a very nice way to provide a constant low concentration of Br2. So if we have our water, DMSO water, and NBS in there, we've got a little bit of Br2, and so our little bit of Br2 will undergo this reaction to make the halohydrin, and since we only had a little bit of Br2 in there, we only have a tiny bit of Br minus, whole bunch of water, the water will do this reaction here. The good news is once this reaction happens and that little bit of Br2 was used up, our equilibrium, Le Chatelier says, oh, we've got to make a little bit more Br2. So N-bromosuccinimide will decompose a little bit, go through its equilibrium to make a little bit more Br2, which will then undergo through this reaction. So N-bromosuccinimide just is a nice way to provide small amount of Br2, so you can definitely make the halohydrin here. All right. What about stereochemistry? Yeah, always got to worry about stereochemistry. Well, no surprises here. We're adding Br2 across a double bond. Bromine will go on one carbon. OH will go on the other carbon. Note, always anti-addition. We've got that bridged halonium, so the water attacks anti to the bridged halonium side. So we've got bromine coming out, OH going back. We will never have bromine coming out and OH coming out also. That would be syn addition, and this is anti-only. but this is chiral, so we have to have its enantiomer here. Note, just like with our epoxides, if we have an unsymmetrical beast here, we have an unsymmetrical bridged halonium, where this attacks the bromine, making this bridged halonium here. Will water attack the more substituted or less substituted carbon? Recall, just like with epoxides, water is a weak nucleophile. This is positively charged up here, just like a protonated epoxide. So just like protonated epoxides, the weak nucleophile attacks the more substituted carbon. And so this will attack here and give us this product right there. All right, that ends this chapter. Cool. We will start the next chapter in the next video.